So let's get started with our transmission line discussion. And I know that some of you may have experienced some transmission line theory before. And so I will do this as a mix of review and emphasizing of new concepts. So the first thing I'd like to mention is that the main reason we're using transmission lines is to actually connect devices. So the way we design systems today is highly modular. So you design one module to do one job and another module to do another job. And that means that you have to connect them somehow. And unless you're using free space waves to connect devices, which sometimes we do, the main way of connecting them is actually by using transmission lines. But unlike DC or low frequency design, where essentially we can just slap two wires and nothing really changes, in RF circuits, putting wires together actually makes a huge difference. And so we have to be incredibly careful of how we do that. So that's why we actually try to understand how we actually connect devices together. Now, there are many, many different types of transmission lines. And in the old days, when there was no good understanding of how things work, the only real way to understand how the signal will propagate through any of those transmission lines is to actually solve Maxwell's equations, right? Which is probably not the most desired thing to do. Since these are three-dimensional equations, and it takes usually a numerical solver to give you any results. The good thing is that today we do have a much better theory called transmission line theory, which is essentially a collection of one-dimensional equations that basically allow you to understand practically all the physics you need of how a signal will basically propagate here. The other thing I'd like to emphasize here is that even though there are many different types of transmission lines, we will mostly be concerned, at least in this class, with planar transmission lines. Mostly because most of the circuits today are actually planar or quasi-planar, or as we will call them, two-dimensional or quasi-two-dimensional. So for example, the line you see right here, which is called microstrip line, and we will spend a little bit of time understanding its main properties, is a planar transmission line. This transmission line, which is called coplanar waveguide, or CPW, is also a planar transmission line. And there are other ones, of course, but these are the most, I would say, dominant ones in terms of how often we utilize them. But three-dimensional transmission lines, like the coaxial line that you see here, as well as the waveguide line that you see here, can also be analyzed using similar techniques. Now, what we actually call transmission line is basically an ideal structure that doesn't really exist in real life. The previous implementations I just showed you on this slide here are essentially realizations that approach that ideal transmission line, but the reality is we cannot make purely a transmission line. And the reason is because we assign a certain number of properties to this transmission line, to the ideal transmission line, that I would like to briefly review because I think it's critical for you to know what these properties are and understand that when you violate one of them, the theory we will learn here may actually not apply. So the first really critical property is that an ideal transmission line only propagates a TEM wave, or a transverse electromagnetic wave, which, if you don't remember exactly what a TM wave is, it's basically a plane wave confined into some type of volume, right? The main reason that we need that is because with a TM wave, we can clearly define voltage. See, you might remember from basic electromagnetics that if you don't have a TM wave, you can't even define uniquely what voltage is. You can actually decide how you integrate the electric field along different paths and actually get a different result. So TM wave is a critical assumption for a transmission line. The second thing is not only it can actually propagate transverse electromagnetic waves, but it actually propagates them without propagating any other mode. In other words, the only allowed mode is the TM mode. No multi-mode transmission lines are basically allowed. No multi-mode effects are basically allowed in the ideal model. Clearly, if you had many modes, many propagating modes, you would have many different effects, For example, multiple propagation constants, multiple phase velocities, and again it becomes a mess. The second critical idea is that this transmission line is purely lossless. That means that the wave can propagate without experiencing any loss. So again, just from this property, you can understand that we can't really have this thing in real life. We always have some type of loss, but the critical thing is that we can have low loss in usual scenarios. And the good thing with low loss is that we can stay close to the theory we're going to learn and simply account for the loss by just adding a little bit of additional details. But our main model will remain the same. Now, loss is also critical because it affects not just power, but as we're going to discuss in a little bit, it also affects speed, which most people don't realize. Most people think that, oh, you introduce a little bit of a loss in a circuit, that means that I only have to supply more power to account for that loss. The answer is no, it actually slows down your circuit if we're talking about a digital circuit. And finally, it's a transmission line, if it's ideal, is a dispersion-free structure, which means that all waves, no matter what frequency, propagate with the same velocity. And that's critical because if there is any dispersion, you will find out that frequencies will have different phase velocities, which will actually lead to group delays. So these are the three main features that define our transmission line model. It's a TM model, it's a lossless model, and it's a dispersion-free model. Again, nothing really gets it ideally, but structures can get quite close to that.